Hey guys, just to let you know, this lesson is in collaboration with Flip Academy, a free online platform for all of your GCSE, A-level, IB and CBSE revision, out now on web at www.flip.academy, and also as an app for Apple, iOS and Android. It really is better than all the other GCSE platforms out there. It covers all the topics in great depth and has an app that you can download your courses on and use offline.
Hello everyone and welcome to Flip Academy. Today we're going to be looking at the probability topic of the AQA specification. So the first one just says using frequency trees and recording frequency of outcomes using a table. So this also ties into one of the later spec points, which is relative frequency, and we'll go through what that means when it comes up. So the title says that 250 trains arrived at a station. The number of trains that were late was recorded after every 50 trains, and this gives us some information about it. So what we need to do is complete the relative frequency graph. So what is relative frequency? Well, relative frequency is essentially, so relative frequency, it's essentially going to be our experimental probability. So what I mean by that is we have two types of probability. We have theoretical probability, so that means in an ideal world, if we were to do this experiment, what would we get as our probability, whereas the experimental probability is essentially what we actually get when we do this test. So as you can see, to get these numbers here, all they do is they take the number of late trains and divide it by the total number of trains. Okay? And if you remember, to work out any probability, all you do is you take the number you're interested in. So in this case, we're looking at the frequency of late trains, so the probability a train is going to be late. So in this case, it's going to be the number of late trains over the total, and that is just the general formula for probability. So if we were to continue this for the other parts, we have 36 late trains, so 36, and we have 150 actual trains, and that gives us 0.24. Next we have 38 over 200, so we don't actually need a thing for that. It's going to be 0.19, because you half it, so 19 divided by 100. And then the last one I will use a calculator for, so that'd be 250 at the bottom, and on top we have 55. That gives us 11 over 50, which is 0.22. So as we go along, right, as we increase the number of trains, that basically increases our number of trials. That will make the relative frequency closer and closer to the theoretical probability. So as the number of trains increases, we're getting a more accurate reading for the probability, okay? Because there's more trials, okay? In this case, more trains. So to complete the graph, all we have to do is at 150, we're doing 0.24, 0.2, and then it goes up in 1, so 1, 2, 3, 4. So it goes up here. And then for 200, we're going up to 0.19, so it's 1 below 0.20. And for 250, we're going up to 0.22. So again, it's going to look like this. It's basically a scatter graph, so you join it with a straight line, like that. Okay. So our actual probability is somewhere in this region. So it says write down the best estimate for the probability that a train arriving at a station is late. Well, as I said, the more trials we do, the more accurate our probability. So the most accurate one is just going to be where we have the most number of trains, which is 250, and the answer to that will be 0.22. So in order to illustrate this a bit better, right, if I flip a coin once, right, what are the probability of getting heads or tails? Well, it's 50-50, right? So it's a 50% chance of getting heads, 50% chance of getting tails, so 0.5 each. Now I can flip a coin and get one heads. I can then flip the same coin again and get another head. That doesn't mean that there's a 100% chance of getting heads. But then the next time I do it, let's say I get tails. So I've got heads, and then tails. If I worked out the relative frequency of getting heads would be 2 heads out of the 3 total. Whereas if I work out the probability of getting tails, it's 1 over 3. Now we know that that's not the case, and it should be a half each. Now, as I do more and more trials, the probability of getting heads and tails will approach half. That's actually one of the later spec points, but it's good to go through now. Now we need to go through a few basically definitions. So we need to apply some ideas. So we have randomness, fairness, and equally likely. So let's define what those mean, okay? So the idea of random, it means that there's no bias, okay? There's no conscious choice. Fair means all outcomes are equally likely. So a best example for this is a dice, right? A dice has the numbers 1 to 6, and the probability of getting any one of those numbers on a fair dice is 1 over 6. Probability of getting 1, 2, 3, 4, 5, 6 is 1 out of 6, because it's fair. Equally likely is similar to fair, but not quite. Equally likely just means that two outcomes or more have the same probability. Of occurring. Okay? Of occurring. Okay? And you're supposed to be able to use this in calculation. So some questions may say a fair dice is rolled, which means you need to make sure the probabilities are the same. Okay? So, relative frequencies to theoretical probability, we just kind of said it. Relative frequency is the actual experimental frequency that you get, and theoretical probability is what you calculate it should be. One other thing to note, and it's kind of shoved in here, but probabilities can only be from 0 to 1. Okay? So that means the fraction has to be between 0 and 1, etc. Okay? Now this should hopefully make sense. If it's 0, the thing is impossible. I.e., it will never, ever, ever happen. What could be less than 0? Right? So this is like flipping a heads and tails and getting a leek or a cabbage pop up. It's not going to happen. Now 1 means it is guaranteed to happen. So if I flip a coin that has heads on both sides, then the probability of getting heads is 1, it's guaranteed. Probability of getting tails is 0, it's impossible. 50, or 1 over 2, or 0.5, whatever you want to call it, means that it's a fair shot. Okay? But that should hopefully give you an idea that probabilities exist on a scale from 0 to 1. Okay? The next one is very similar to this. It's that probabilities sum to 1, right? So if I add up all possibilities, the probabilities of them happening should add up to 1, right? Now if we think about what that means, it means that if I add up the probability of anything happening, so when I do something, something happens, it should be 1. Because guaranteed that something will happen. And you get questions like this. Okay, so again, this is from the 2021 paper, it's paper 3. So a biased spinner. So biased means that it's not fair. So all probabilities are different. It can land on A, B, or C. It gives us in terms of K, probability A, B, and C. It says work out the probability of B. Problem is, we don't know what K is. However, we know that if I take the probability of A, add the probability of B, and add the probability of C, that needs to equal 1. Because if I spin this spinner, which has 3 letters on it, it should land on one of them, right? It can't land on none of them, so it equals 1. So then all we need to do is add all of this up. So that would be 3k, so that would be 10k minus 0.15. 1. Yeah, that's correct. So then 10k equals 1.15. Therefore, k is equal to 0.115. So that means the probability of getting B is just equal to 7 times 0.115 minus 0.15. Okay, which I'm just going to use a calculator for that, because this is definitely a calculator question. We have 0.115 minus 0... Oops. Cool. That gives me 0.655. Yeah. If you ever get a probability greater than 1 or less than 0, you are definitely 1000% wrong. Okay. So, this is again something that I went through just now, right? Is that if you have so empirical just means experimental, right? So it means when you actually do it, the theoretical probability, so it will approach the theoretical probability, okay? The relative frequency will approach that. So the idea is that if you take a sample and you do something, increasing the sample size makes the probability more accurate, always. And by probability, I mean the relative frequency. More accurate. Okay? So, again, if you're really, really bored, right, if you flipped a coin 10 times, right, it's very unlikely that you'll get 5 heads and 5 tails exactly. However, that's what you expect, right? There's a 50-50 chance of getting a head or a tails. You expect to get 5 heads and 5 tails, but if you do it, you'll find that you'll actually get a different value. You'll get maybe 3 heads and 7 tails or something like that. Now, if you did it 100 times, you'll get closer to a 50-50 shot. Did it 1,000 times, closer again. And if you were to do it 1,000,000 times, you should get 500,000 heads, 500,000 tails. But it approaches that. It gets more and more accurate, okay? So, in questions, they can ask you, how do we improve the reliability, or which probability is the most reliable? It's whatever one has the most number of trials associated with it. Okay, that is the very, very key thing to remember. The next thing is basically Venn diagrams and sets. So Venn diagrams look like this, and they represent the different sets, right? So this big circle here represents, in this case, all of the singers, S, and this G represents all the guitars. And this overlap will be the people that sing and play guitar. Outside of this will be everyone that does not sing and does not play the guitar. If that makes sense. So here's some information. About 80 people. So we know in total there should be 80 people, okay? They should all add up to 80. Now it tells us that 12 are singers but not guitar players. So that goes in here. Because this region here, right, not the whole circle, but this bit, are people that sing but don't do anything else. Okay? 30% are neither a singer nor a guitar player. So what we have to do is take 30% of 80, which is 24. So 24 people do neither, which would be outside here. So at the moment we've got 36 out of 80 people, that's good. And then it says a quarter of the guitar players are also singers. So you might think, okay, that's a bit weird. Why are they telling me that? Well, the number of guitar players is just going to equal 80 minus 24 minus 12, right? Now let's think about why that works. Actually, first we'll work it out. So 80 minus 36 was 44. Now why does that work? Well, if they aren't singers, right, and they aren't nothing, they have to play the guitar. Okay? Now it says a quarter of these guitar players are also singers. So a quarter of 44 is 11. So there are 11 people who sing and play the guitar, which means everyone else is just a guitar player. So if we were to add all of this up, it should add up to 80. So 33 plus 11 is 44. Plus 12 gives me 56. Plus 24 gives me 80, so I know I'm right. So the best thing to do at the end of a Venn diagram question is to add up all of the numbers to make sure it equals the total. And that's 4 marks. You get a mark for... you lose a mark for every number you get incorrect. Okay? So you don't really gain marks as much as lose them. Okay, so hopefully that makes sense. And constructing theoretical probability spaces, essentially, if I say I flip a coin 4 times, actually say 2 times for now, calculate the probability of getting 2 heads. One way to do this is to create something called a theoretical probability space. So what you do is you say, what are all the possibilities? So the first possibility is obviously I get 2 heads. Next possibility, I get a heads, then a tails, then a tails and a heads, then a tails and a tails. So this is my desired outcome. There's only one desired outcome. How many do I have in total? 1, 2, 3, 4. So my probability is 1 over 4, because there's only one way I can get 2 heads when I flip a coin twice out of 4 possibilities. This thing I've drawn on the left is a theoretical probability space. It's not really a formal thing, so it's not really something that I'll say, construct a theoretical probability space. Instead, it's just something you can use to work out an answer. Okay? Likewise, if I said, what's the probability of getting a heads and a tail? I'd say, well, there's 2 outcomes like that, so 2, and there's 4 total, so that's a half. The probability of getting 1 head, 1 tail. Right, I can get a head and a tail, or I can get a tail and a head. Okay. Not much more left. Calculate the probability of independent and dependent combined events, including using tree diagrams, and know the underlying assumptions. Okay, so this is quite an interesting one. Probability trees, a lot of students like them because they're not too bad. I quite like them myself. This is the one from the 2021 paper 1. And we read through this. Okay, items made at a factory have to pass 2 checks. 90% pass the first check, so 0.9. The key thing to remember is across branches, probabilities have to add up to 1, right? Think about it. If it doesn't pass, it fails. So those probabilities should add up to 1 because it passes or fails, there's no mix. So 1 minus 0.9 would give me 0.1. The items that fail are scrapped, which is why there's nothing else up here, right? It doesn't go on to the next check because it's deleted, gone. 99% of the items that pass the first check also pass the second. So 99%, let's draw the 0.99. So the probability that it fails is 0.01. Okay, so across branches, it needs to add up to 1. Nice and easy. It then says an item is chosen at random before the checks. Work out the probability that the item is scrapped. Okay, so here's where things get a bit more spicy. There are 2 ways an item can be scrapped. It either gets scrapped straight away, so the probability that it fails straight away, or it can pass, then fail. Now when I say the word or in probability, I add them together. Because it's this or this, so my probability increases. If there's multiple ways for something to happen, the probability has to increase. Okay? So, probability that I fail is 0.1, not I fail, the thing. Probability that it fails the second time is 0.01. So in total, the probability that it's scrapped is 0.11 for 3 marks. Okay. So again, 1 for each of this and 1 for getting the right answer, because people sometimes times instead, but you just need to add. If anything has the word and in it, you times. Okay, so if it said what's the probability that it passes and it fails, right? So that's what we have so far. So if you notice, pass and fail, I would need to also times this. I haven't actually left myself enough space. So that's where this would be incorrect, right? I'm adding because there are 2 ways this can happen. But this one, and this is a common mistake, is that they just add this probability. It has to pass and fail afterwards. So it would be 0.9, and the word and means we times. Okay? Just to go through that again. I have the word or because I either fail or I pass then fail. So I add. But to do pass and fail, I say pass and fail, right? So I do the pass and I fail, so I multiply it. So in general, when you're going across branches, it needs to add to 1. When you're going along them, you need to times the probabilities together. So now we can put this into our calculator to actually work out what on earth our answer is. And we have 0.1 plus, open bracket, 0.9 multiplied by 0.01, and you get 0.109. So again, you get a mark here, a mark here, and a mark for getting the right answer. Because again, most people would get that incorrect. They would multiply either these 2 together or forget to multiply this. So be really, really careful. For hire only, and this is the last point as well, so it's a bit of a shorter topic, we need to calculate and interpret conditional probabilities using two-way tables. Okay, so, and there are a few ways to do this. So this is from the 2021 paper 2. So 20 people asked which device they use more often, laptop or phone. This is the response. So, one male and one female are chosen at random. Work out the probability that exactly one of them said laptop. Right. So, two possibilities, right? We have a possibility that the man says laptop. So let's write ML, man laptop, right? And the woman is, so woman phone, right? Or the man says phone and the woman says laptop. Those are my two possibilities, right? So if you want, you can we can make that theoretical probability space. So all of our options are they both say laptop. The first one says laptop. So again, if we say this is men and this is women, so both say laptop, laptop, phone, then it can be phone, laptop, and then it can be phone, phone. So the ones that we're interested in are these. Okay? Now, of course, this doesn't mean that my answer is 2/4. Because it's not a fair situation. It's not a 50-50 shot if they pick laptop or phone. Because if we have a look, these numbers are all different. They're skewed. Men have far fewer laptops than phones, or they've voted for it less. And women, they're a bit more closer to 50-50. So we can't say it's just 2/4. Because they aren't equally likely. This isn't like throwing a coin. Okay, it's not equally likely. So, let's work it out. The probability that a male says laptop is going to be 2 out of 2 plus 9, 11, because there are 11 males. Okay? And, right, because we also need the woman to say phone, so and we're going to multiply by the woman saying phone, so that's 5, because we're looking at the people that said 5, over 4 plus 5, which is 9. Then we have the word or, which corresponds to a plus when we're talking about probability. So man says phone, that's going to be 9 over 11. Multiplied by woman laptop, that is going to be 4 over 9. That is going to be our final answer. And again, technically we could do this. Actually, let's just do it with that calculator. Some probability questions aren't calculator, okay? In general, if they have decimals in it, they're calculator. If it's fractions, they expect you to do it non-calculator. So 2 times 5 is 10. 11 times 9 is 99. Plus 9 times 4, which is 36, over 99 again. So we get 46 over 99, which is our answer. Okay, so that brings us to the end of the probability section. So again, it's a much shorter section on the spec. However, it tends to be quite a tricky one because it's a bit more nuanced. It's a bit abstract as well. So just make sure that you go over it as much as possible, and I look forward to seeing you in the next one.